Vector semantics starts with a hypothesis, which is called distributional hypothesis. It says that words that occur in similar contexts tend to have similar meanings. So if you think about it, it's actually analogous to people. If you know a person, let's say his or her name is A, and then A's friends are mostly college students, you may think that A is also likely to be a college student. For example, you know another person, let's call him or her B, and then you also notice that most of B's friends are college students. So now you can think that probably B is also college students, and then A and B are both college students. So in other words, a lot of times you may infer somebody's characteristics based on his or her surroundings, like his friends, the people whom they make a lot of contact with, the things that they read, their hobbies, and so on. So it's the same case with words. You usually can tell what a word means or what that word infer based on the words surrounding that word. Now let me give you an example. Suppose you're taking TOEFL test and then you see some words that you don't understand. You've just never heard of those words at all. But you need to guess the meaning of those words because you need to answer the questions. Like here, for example, I give you the word ong choi. Can you guess what it means? I also give you some examples of the sentences that contain the word ong choi. A sentence that contains the word spinach, which I'm sure you're quite familiar with, and there are two other sentences. You may pause the video to read the sentences carefully and then guess what ong choi means. Well, we may start from the fourth sentence. From the fourth sentence, we're familiar with the word spinach, and you see it appears together with the word garlic and rice. So ong choi also appears together with the word garlic and rice. So you might start thinking that, okay, probably it's something like spinach. Let's take a look at the other two examples. Here, sentence 5, it says chard, stems, and leaves are delicious. Okay, so chard is something that has leaves and stems, and it is edible and it is delicious. And then at sentence 6, it says collard greens and other salty leafy greens. So from these sentences, you see that, okay, so ong choi is something that is edible like spinach, and it is similarly cooked with garlic and served over rice. And then it also can be served with salty sauces. So you can see that, okay, probably collard greens is also kind of vegetable. Same thing with chard stems, it's also a leafy vegetable. So that kind of process helps us to infer the meaning of words. And so actually, yes, ong choi is kind of vegetable, and in Indonesian language we call it kangkung. And then chard and collard greens are also the other types of vegetables. Let me talk a little bit about a vegetable. It just made me curious because this vegetable has so many names. In Indonesian language, we have one name for that. It's called kangkung. However, in English, we've seen ong choi. I've also heard o choi, hollow vegetable, hollow spinach, and water spinach. Talking about all this hollowness of this vegetable, probably it comes from the Chinese name for this vegetable. In Chinese, it is called kong xin chai. Kong means empty, xin means heart, and then chai means vegetable. So if you translate it literally, it means that this vegetable has an empty heart. It sounds kind of quite interesting, romantic, but let me get back to our topic about vector semantics. So we just saw how we can infer the meaning of a word based on the other words that surround that word. So that is distributional hypothesis. So what we are going to learn in the topic of vector semantics is that we are going to represent the meaning of the words in terms of vectors. So we have words, the words have meanings, and we want to represent those meanings in a vector. How can we do that? Well, we'll see that we'll use the idea that we just did, which is distributional hypothesis idea. We infer the meaning of a word based on its surroundings. And vector semantics is also called word embeddings because it means that we're going to embed the meaning of a word in a vector space. We will start by looking at two types of semantics, lexical semantics and vector semantics. Let's start with lexical semantics. Semantics is a linguistic study of word meaning. In other words, it studies what word means. A word can actually have multiple meanings. So for example, in English, the word mouse can mean the animal. It can also mean a computer device. So for each aspect of the meaning of a word, is it called a word sense. So for the example of the word mouse, it has two word senses. The first sense corresponds to the animal. The second sense corresponds to the computer device. Defining the meaning of a word is certainly difficult. However, there are some aspects or properties that are related to word meaning. The first aspect is called synonymy, in which there are two senses of two words have identical meanings. So these pairs of words, couch and sofa, vomit and throw up, filbert and hazelnut, car and automobile, they have identical meanings. In reality, many words do not have synonyms. It means that there are not many words that have the other word that have identical meaning. However, most words do have lots of similar words. So not identical, but similar. So the table here shows the pairs of words and then how similar they are. On the top of the list, vanish and disappear, they are very similar. You might even say they are identical. Behave and obey, they're kind of similar, but not so identical. And then at the bottom of the list, there are a pair of words, whole and agreement, which you might say that they are very not similar to each other. The next aspect is called word relatedness or association. So these three words, waiter, menu, and chef, they are neither synonyms nor similar. However, they are related. You might say that these three words are related to a restaurant. The next aspect of word meaning is called semantic frames. It means that you may describe one activity from different perspectives. For example, in the activity of trading things, you might describe that activity from the buyer's perspective, A buys the thing from B, or from the seller's perspective, B sells the things to A. The words may also tell us about the roles of the people involved in that activity. In the example, Sam bought the book from Ling, we know that Sam is the buyer and Ling is the seller. Finally, words may have connotations. It means that when you see or hear a word, you might feel something about that word. It may describe by these three properties: valence, arousal, and dominance. Valence shows how pleasant a word is. For example, happy is a pleasant word, annoyed is an unpleasant word. Arousal shows the intensity of the emotion. For example, either you're frenzied or you're relaxed. And dominance shows the degree of control exerted by the stimulus. These tables show the values of valence, arousal, and dominance for these several words. Now, the importance of these words and their values of valence, arousal, and dominance is that now You may represent each of these words in a three-dimensional space. Let's take an example. Imagine valence is the x-axis, arousal is the y-axis, and dominance is the z-axis. So the word music equals to a point of 7.67 in x-axis, 5.57 in y-axis, and 6.5 in z-axis. So for any of these words, you may represent these words into a dot in a three-dimensional space. So what I just described is an idea of vector semantics. So it uses the value of the valence, arousal, and dominance of a word to create a representation of a word in a three-dimensional space. However, can we build a model that successfully deals with all different aspects of word meaning? Not just the connotations like the valence, arousal, and dominance that represent the connotations, but can we also build a model that deals with word senses, similarity, semantic roles, semantic frames, and so on? Well, the answer is apparently up to now, a perfect model turns out to be elusive, means that we don't have that kind of model yet. The current best model is vector semantics. And then we have seen one idea how to create the vectors, and in the rest of the presentation, we'll see what are the other ideas to create the vectors. Here you see a figure that shows an example of vector semantics. So each of this word here is a position in the x and y axis. For example, you imagine this is the x-axis, and then that is the y-axis, and all the words here are plotted as a dot in x and y axis. You see that this model is quite good because it may group together the words that have positive meanings. For example, fantastic, wonderful, nice, good, and so on. It can also group the other words that have unpleasant meanings, like dislike, bad words, and so on. And then it also has another group of words that contain the words that are usually used in any word, whether it is a positive, in any sentence I meant, whether it is a positive or negative sentence. So these are the vector semantics, and we're going to learn how can we create these vectors. So we have seen one idea on how to represent the meaning of a word in a three-dimensional space, which was using the value of the valence, arousal, and dominance. Now we are going to take a look at the other idea, which uses co-occurrence matrix. So co-occurrence matrix is a matrix that records how many times words occur together. So we count how many times word A and word B occurs together, and then we record that frequency in the matrix. So for example, there's a matrix called word-word matrix, because this is a square matrix, and then the number of the rows equals to the number of the words in your vocabulary. The number of columns also equals the number of words that you have in the vocabulary. So in this example, let's say you have n words in the vocabulary. So the rows starts from word 1, word 2, up to word n. And the columns also starts from word 1, word 2, up to word n. And then the entry of each cell means that how often you see word 1 occurs with word 2 together in your document. So here the value should be how often word 1 occurs together with word 2 in your document. So here is an example of a co-occurrence matrix or word-word matrix. but it is truncated here, so it only shows 4 words in the row, and then it only shows several words in the column. Remember, if we are looking at the complete word matrix, the number of rows and the number of columns should equal to the number of words in your vocabulary. So it must be a very huge matrix. Okay. Now, technically, how can we compute this number? For example, you see cherry and computer appears together twice. Does it mean that they appear together in a sentence, in a paragraph, in a document, or what? Well, usually as the basis to compute how often 2 words appear together, we use something called as a window. So here in the example, we use the window of 4 to describe the context. It means that, let's say we are at this word cherry. The context of this word is 4 words to the left and 4 words to the right. And all these words, 4 to the left and 4 to the right, is called the context word of the cherry. So now to compute the co-occurrence, or how often word A and word B appear together, we just look at the context of the word. So we look at the context and calculate how often word A and word B appear together. Now, once we have the word matrix, actually now we are able to model each word into a vector. So for example, now you may represent the word digital in a vector of containing the value of 0, 1670, 1683, 85, 5, and 4. We may also plot the words to see how similar they are in the meanings. So here the x-axis is the word data and the y-axis is the word computer. It means that in the x-axis, the value will represent how many times one word appears together with the word data, and then the y-axis would represent how many times a particular word appears together with the word computer. So let's say the word is information. So information appears together with data 3,982 times, and then appear together with the word computer 3,325 times. So the point is here, and that is the vector. The word digital appears 1,680 times together with the word data, and then it appears 1,670 times together with the word computer. So the point is here, and the vector is that. So what can we say based on this graph? Well, we can say that in the context of data and computer, the words information and digital have very similar meanings. Why? Because the vectors of information and digital, they almost point to the same direction. It means that they are very similar vectors, so we can say that the meanings are very similar as well. Previously, I said that the words digital and information have similar meanings because their vectors point to the very similar direction. So to formalize the idea of similar vectors, actually there's a quantitative metric called cosine similarity. So if you have two vectors here, v and w, you may compute the cosine similarity using this formula. On the top part, you do the dot products of the vectors, and then on the bottom part, you take the multiplication of the length of each vector. By dot product, I mean you simply multiply the elements of the vector in the corresponding positions, and then to obtain the length of vector, you take the sum of the square of each element of in the vector, and then you take the square root of that sum. So here in the figure you can see that suppose we have three vectors, cherry, digital, and information. Using the cosine similarity, we may have a quantitative value saying that how similar those three vectors are to each other. Now here's an example. Suppose we have three words, cherry, digital, and information, and then each word is represented by a vector of 3 dimensions. Now your task is to compute the cosine similarity between the word cherry and information and between the word of digital and information. You may pause the video and do the calculation. So this is the answer. The similarity between cherry and information is 0.017. The similarity between digital and information is 0.996. What can you infer from this result? You can say that the words digital and information are much similar to each other, but then can you also go on like, why does that happen? Or why this cosine similarity can measure that the words digital and information are actually much more similar than the words cherry and information. Why can that happen? Well, the clue is that we've been using the co-occurrence or word-word matrix. So what we've seen so far is that we're using the frequency to fill the co-occurrence matrix. It means that we compute how many times we see word A and word B occurs together. However, when we just use the frequency, I call it raw frequency here, sometimes there are words that are too rare. This word just appears, let's say, once or twice in your entire document, and then as the result, the appearance of that word with all the other words are mostly zeros. So you have a lot of zeros and only several entries of 1 or 2. That is not very informative for your vector semantics. On the other extreme, you also have words that appear too frequently. For example, the word the word it, they appear so many times, and they appear together with almost any words in your vocabulary. Again, if it appears too often, then it's not really informative to make a differentiation between word A and word B, because these kind of words, they always appear together with whatever words. So there's a suggestion or idea to use something called Tf-idf instead of raw frequency. It stands for term frequency inverse document frequency. It's quite simple actually. So first we compute the term frequency. It simply means the frequency of the word T in document D. So for each document that we have in the corpus, we have to compute the term frequency of particular term. So let's say you have 10 documents. So for term T or word T, you have TFT1, TFT2, TFT3, up to TFT10. And then for the document frequency, you compute the number of documents that word T occurs in. Then we take the inverse. So here, if you look at the equation, DFT here means how many documents contain the word T. And then we take the inverse by put this n, the number of documents that you have on the top, and then the DFT in the bottom. You may take a log for that value. So that becomes inverse document frequency of the term T. And then what we can do to replace the raw frequency with the Tf-idf is simply we take the multiplication between the term frequency and the inverse document frequency of the term t. So now instead of the row frequency, we use the Tf-idf. Now let's take a look more closely to the Tf-idf formula. The first term is quite straightforward. Term frequency, the more often a word appears, the term frequency value is the higher. However, for the second term, IDF, if a word appears too often, then the IDF score is low. Let's take a look at the example from 37 Shakespeare plays. The word good and sweet, they appear in all documents, such that their IDF score is 0. Why is this the case? Well, if a word appears in all documents that you have, or even more extreme, let's say in all sentences that you have, then those words are not informative to help you determine the meaning of word A and word B based on their co-occurrence with these words. It's the different case, let's say if the word Romeo only appear in one document, then if you have word A and word B, you might be able to tell the difference in the meaning of those words based on how they co-occur together with the word Romeo. Because Romeo appears not very often, so it helps you to differentiate what are the meaning of the word A and word B. So to recap, if you want to have a high Tf-idf score, it means the word should be high in frequency. It also should be high in IDF score, which means that it appears quite often, but not too often. Because if your frequency is high, but your appearance in all the documents is too often, then your IDF score will be low, and the overall score will be low as well. So let's take a look at the comparison between using the row frequency and then the Tf-idf value. Here I'm showing you a different idea to fill the co-occurrence matrix. So here the rows are the words. So you have the word battle, good, full, and with. However, the columns are the documents. So each of this column is a Shakespeare book or play. So you have a play title As You Like It, Twelfth Night, Julius Caesar, and Henry V. So this is another possibility to build a co-occurrence matrix. So let's see here the word good, it appears 114 times in the book As You Like It, 80 times in the 12th Night book, 62 times in Julius Caesar, and 89 times in the Henry V book. That's the row frequency. However, as we've seen before, this word is just too often. It appears in all Shakespeare plays. So to reflect that kind of fact, we use the Tf-idf, and you see here now the score for the Tf-idf score for the word good becomes 0. Why? Because it appears too often such that it doesn't help us to differentiate between the meaning of the words that we have. On the other hand, let's say if we have the word battle, even if it's not very often, but in the Tf-idf, the score becomes quite high. So the idea of Tf-idf is to penalize the words that appear too often. It also takes consideration of the frequency. So it takes care of the words that are too rare and too frequent as well. If you've been with me this far, now let me give you an optional quiz. So we've seen before that we use the window of 4 to create the co-occurrence matrix, or the word-word matrix. Now I'd like to ask you, what would be the effect on the vector semantics if we set the window either narrower, for example, just one word to the left and one word to the right, or we set a very wide window. For example, when we say 2 words co-occur or occur together, we say that when they appear in the same sentence, then we just compute them as occurring together. Now, what would be the effect on the vector semantics? Especially, I would like you to think whether this will cause the vectors to become more accurate in representing the meaning or more inaccurate, or whatever effects that you think this might happen. Okay, so if you'd like to get extra points, send your answer through IDA message, and then the first 10 answers that make sense will get extra points. So you don't really have to worry about whether your answer is correct or not. Of course, you can always Google things to find out the information and read the stuff, but as long as your argument making sense, then I think I will give you extra points. So there are 3 takeaways from this section. First, words may be represented by co-occurrence vectors, and then if you put these vectors together, it becomes a co-occurrence matrix. And there are several ideas or ways to create this co-occurrence matrix. And then the second takeaway is that the co-occurrence may be represented by either row frequency or Tf-idf. You have to understand what's the idea behind Tf-idf. And then the third takeaway is that the similarity between vectors, which represents the similarity between word meanings, may be measured by cosine similarity. Now, if you have any question, feel free to leave your question in the comments or shoot me an email or leave me a message in IDE. Thank you.